Hey guys! In this video, we're going to talk about exponential and logarithmic differentiation. Now, some of these properties and rules for exponents and logs you may or may not remember, so it might be a really good idea to go back and remind yourself of some properties. For the basics, I gave you some graphs and the properties of the functions themselves. One of the key things to remember is that a logarithm is the exponent of an exponential function. So if we're dealing with y equals some number to the x power, then the corresponding inverse will be a logarithm. So a lot of the properties between exponentials and logarithms are direct inverses of each other, which is how we start with our differentiation methods. And you can look at these properties as you wish to remind yourself of things. So for the differentiation part, we start with, what do we want to do? Well, if y equals the natural log of x, this only works if x is e to the y power, because we're starting with the generalization. So if we have x equals e to the y, and we want to take the derivative of this, we do implicit differentiation, which we learned about in last section. Well, dx of x is just 1, and then ddx of e to the y would be e to the y times the derivative of the exponent, which would be dy dx. So simple division would give us 1 over e to the y equals dy dx. And we started with x equals e to the y, so 1 over x would be dy dx. Now, admittedly, this is a very generalized form. It's very general. Not to mention, we are using e instead of just any generic number. But this is the general idea of how we do it for more complex things and how we got our three formulas using implicit differentiation and then the chain rule. So with that, we have these lovely formulas. So let's actually work with them. The easiest one I know of is that the derivative of ln x is 1 over x. If you want to do the chain, which is this third one here, we can if we need to, which we do in this first one. So d dx of 7 ln 15x, well, that 7 can come out front of ln of 15x, but then we have the chain rule. So u would be 15x, and then du would be 15, also known as u prime. Careful of your notation, but also make sure that you know what means what. So that 7 is not going anywhere. And then we have, according to our formula, our u prime, or du dx, would be the 15, and then times 1 over u, which is 15x. The two 15s will cancel. Anything over itself is 1. So that gives us our final answer of 7 over x. Most things are like this, especially if we follow these lovely formulas. They're just faster than doing it with implicit differentiation. But we'll get to that with the more complicated ones anyway. So I figured we'd start with the nice ones. Let's look at the next one. So the derivative of the natural log of sine x. Well, once again, this is the chain rule. If we have u set up as sine x, then u prime, or du dx, either way, the derivative of sine is cosine. So we have, according to our chain rule says that dy dx is dy du times du dx. Well, if u is sine x, then y all of a sudden becomes the natural log of u. So dy du would be 1 over u. So 1 over u times du dx, or u prime, would be cosine of x. So 1 over our u is sine x times cosine x, which is cosine x over sine x, otherwise known as cotangent x. That's a very long-winded way of doing that problem, but it does work. Now, let's do the exact same problem, but let's do it slightly differently. Instead of using dy dx with the chain rule, let's use that third formula. It's still the chain rule. This third formula is the chain rule, I promise. But it's using slightly different notation. So let's do that. So by the formula, we would have that dy dx would be u prime over u. So u prime, we already found as cosine x, over u, which is sine x. Cosine over sine is cotangent. Much faster, much easier. But whatever makes the most sense to you is the best way to do it, whichever way. Let's do another one. So here we have the lovely product rule. Split right down the middle. We have, there's f, and there's g. Product rule says f prime g plus f g prime. So if f is 5x to the 5th, that means that f prime is the power rule, so that would be 25x to the 4th. G would not change, so that's just natural log of x plus f. And then g prime would be the natural log of x. Its derivative would be 1 over x. And there's actually just not much you can do with that. You can't really simplify it very much. We can do a little bit, though. The first term is not going anywhere. But we can say that x to the 5th over x is x to the 4th. So with these formulas, it makes our lives a lot faster, in general. Now, these were the generalized formulas for the derivative of the natural log. But how about the derivative of exponentials? It'd be the same thing we were starting with, except we're working backwards. And you can check that on your own if you so wish. So for here, and this second one is just a more generalized form of the chain rule, but it's the same thing. This one is the one we haven't seen before. So let's use that. So this example 4 here we have is the product rule again. So if our first is f, and this would be g, then f prime would be 7x to the 6th times g, which is 6.5 to the x, plus f, and then g prime. This is where our formula would come in. So that would do 6.5 to the x power natural log of 6.5, according to our formula right there. Now at this point, we look at it and say, can we simplify that? And the answer is not really, no. So this lovely thing, all of it is g prime, because that's pretty much as good as it's going to get. Now, of course, things do not stay so nice and easy. So let's take a look at example 5 here. So if f of x is x to the sine x power, and we want to find f prime of pi over 2, well, first we have to find f prime of x. This is not nearly as nice as it looks. You could sit here for ages staring at it, and it doesn't really work. What we do is we have to use a trick. So using our exponential and logarithmic properties is where this comes in. We can rewrite any number, b to the x power, as e to the x natural log b, using exponential properties and the definition of a logarithm, and it works. So we're going to do the exact same thing here. Instead of having f of x equals x to the sine x, we're going to rewrite that as f of x to e to the sine x times the natural log of x. And we can do that using that definition property. Now, because of this, and now we have that lovely e there, which makes it all work, we can find the derivative using the chain rule. If we set u as our exponent here, sine x ln x, then we can use the product rule to find its derivative of u prime. So, derivative of sine is cosine times ln x plus sine x times derivative of natural log is 1 over x. So now we can use that with the chain rule. So f prime, based on the chain rule, is e to the sine x times the natural log of x times u prime. Remember, because the derivative of e to any power is just e to that same power. So multiply that by u prime. And then we want to simplify as much as we can, but there's not much we can say. The only real thing we can say is, well, we can switch it back. We had f of x equals x to the sine x, and then we changed that to e to the sine x times ln x. So we can rewrite that portion of f prime of x to x sine x times that lovely same cosine, because there's not much we can do there. It's not pretty, but it works. Of course, that's not actually the question they ask us, is it? They wanted us to find f prime of pi over 2. So let's do that. So f prime of pi over 2, anywhere we see an x, we're going to put pi over 2. Simple substitution. Don't try to simplify yet. Just do simple substitution. Okay, now take a look. What do we know? What can we find? Well, immediately on my brain is that the sine of pi over 2 is 1. So that goes to 1, and that goes to 1. That makes our life easier. And I also know that cosine of pi over 2 is 0. So that goes to 0. Awesome! I like zeros and ones. So let's take a secondary look. So that'd be pi over 2. And then, well, 0 times anything is just 0, so that first term goes to 0. And that'd be 1 over pi over 2, otherwise known as 2 over pi, right? Which means we did a whole lot of work to get 1. But at least we're not simplifying some crazy fraction. So now we need to talk about the more generalized formula, because we started with the derivative of the natural log. Well, the natural log is very compartmentalized. It's very, very specific. Your base is e. So finding the natural log, 1 over x, is not that bad. But you're not always going to have a base of e. If it's any other base, you're probably going to be looking at an actual log instead of a natural log. And thus we have these two other formulas. These are for the most generalized version of finding a derivative of a logarithm. And application is just as before. So if in this lovely example 6 log base 6 of x, and we want to find the derivative, then according to this formula right here, we're going to take the of x part, that'll be right there, and then the natural log of the base, in our case 6. And that's it. Ta-da! All done. At least for that one. So let's do one slightly harder. How about 5 times the log of 5 of x to the 4th minus 5? So we want to do this as well as we can. So the first thing that I notice is I will end up doing the chain rule. So if u is x to the 4 minus 5, then du, or u prime, would be 4x cubed. And I can break this down into 5 times log base 5 of u. Which makes it easier on me. So my dy dx, according to my formula, that'd be 5 times, because we always can push the coefficient out front. The derivative of dy du would be 1 over u times ln 5 times u prime, 4x cubed. So let's simplify this a bit. So I get 20x cubed over x to the 4 minus 5, because that's what our u is, times ln 5. And there's just not much else I can do. So in a lot of cases for these logarithmic derivatives, there's only a few steps to them. So don't get bogged down too much and start second-guessing yourself. Now the last thing we need to talk about is if something is not so nice. So let's see about this. This is definitely not nice. It's not even close to nice. I look at it and my brain kind of wants to go to the side and say, huh? Well, we can still find the derivative, but we have to do some finagling using logarithms and logarithmic properties. So the first thing that I'm going to do is I'm going to take the natural log of both sides of my equation, and I'm going to use logarithmic properties to simplify this as much as I can. So let's get rid of everything I can think of so that I can look at it way prettier. So the first thing that I notice, and make sure that we have the right label, that this is the natural log of f of x. Well, if you have the logarithm then you can subtract them. Same thing if you have multiplication, you can, add them, split them up. This is logarithmic properties. And the last logarithmic property is if you have an exponent, which you can then pull out front. So I'm going to use those three properties to my best advantage. The first thing I notice is that I'm using division, so I can fix it and get them into subtraction. So that would be the natural log of x plus 2 to the 11th minus the natural log of 4x minus 12 to the 19th. Now I don't want those powers there, so I can use this third property to pull the powers out front. So 11 times the natural log of x plus 2 minus 19 natural log of 4x minus 12. See, that looks so much better. So much better. At the very least, I only have to write one line. So now let's try to take the derivative. Well, using the property chain rule of natural log, well, the chain rule property of natural logs says that if I take the derivative, I'm going to get u prime over u, right? That's what the lovely thingy said way, where was it? There. Nope. There. Here. So, the derivative of the natural log of f of x will be f prime of x over f of x. Okay, so we're going to use this to our advantage with this problem. Let's go back. There it is. Okay, so let's take d dx of everything. Whee! Okay, so my left side, according to the chain rule, says I will have f prime of x over f of x. So now let's finish it. According to the rule for derivatives of natural logs, that would be 11 times 1 over u, so x plus 2, 1 over whatever is in our natural log parentheses, times the natural log of, times the derivative of the inside. So the derivative of x plus 2, which would be 1, right? And then minus 19 times 1 over 4x minus 12 times the derivative of my inside, which would be 4. Okay. Simplify as much as possible. So we get 1 times anything is just that. And then I can actually pull out a 4 in this denominator here. And then 4 over 4 is 1. So this second fraction becomes 19 over x minus 3, which is wonderful, because our left side still says that f prime of x over f of x, which means I can actually solve for f prime by multiplying by f of x, and then multiplying whatever f of x is to this lovely derivative of my right side that I just found? Well, we know what f of x is because they told us way back here. There, that's f of x. So substitute the f of x there for the f of x that they gave us, and we'll be done. And there we are. So it's definitely not nearly as pretty as using the formulas that we had before, but we can still make it work. So be careful, go step by step, don't miss any steps, and follow the logarithmic properties. If you need to make a separate sheet with those properties on them and all the different properties and all the different formulas, then do so. It's always handy.